Yes, today we continue with our machine learning project. Previously, we looked at the EDA, where we did a deep study into our data to know if there is an imbalance, what classes we ought to give a higher weight, and so on and so forth. So for today, we will be looking at methodology and system architecture. And since I'm looking at a video data set, my concern or my choice of models today is the convolutional network combined with long short-term memory as my first choice of model architecture. So to begin with, when you come to CNN plus LSTM, these are two neural network techniques that you can use to analyze surveillance footage, for example, like our data, and classify them into the necessary categories. Of course, the model will begin with video input, where it receives raw surveillance video footage from the data set. And since neural networks cannot process the entire videos directly, the video is first broken down into individual frames, which will take us to the next step, and that is frame extraction. And when it comes to frame extraction, at this stage, when we come to our video, we are going to extract a sequence. We are going to extract image frames we are going to randomly extract image frames from our video, but we are going to extract a fixed number of frames per video so that all the inputs into our model are of the same size. And this is important because it ensures that the neural network receives consistent input during training. And when we go to the next step, after we have extracted our frames, we want to extract features from each of those frames, which we called CNN feature extraction, which is the third step. And here, each frame will be passed through the convolutional neural network. For our case, which was a pre-trained CNN, I used the ResNet 50, which is a pre-trained CNN. And this CNN extracts spatial features from each of the frames. And these include visual patterns such as objects, people, vehicles, broken windows, or unusual movements. For example, it may detect a person standing near a car, a person's arm raising, a person's arm that is raised, for example, I guess, that is raised and holding an object. Yes, so that is step 3, where we extract features from each of the frames. And then we go into sequencing, which is the long short-term memory part, and that is sequence processing. After we have extracted features from each frames, we want to arrange those features into a sequence and then pass that sequence into the LSTM network. So we pass the sequence of frames into the sequence of features into the LSTM network. And here, it's basic. When you come to LSTM, is long short-term memory. It's basically a recurrent neural network. It's the same as CNN, only that it is recurring and it's designed to learn patterns over time. So the importance of this is for the model to analyze how events unfold across multiple frames. For example, it can recognize a sequence, let's say, such as a person approaching a vehicle or breaking a window. It recognizes it over time. And that will bring us to that, which is our fully connected classification layer. And here, the output from the LSTM is passed into a fully connected layer, and this performs the final classification. For example, the model can predict that according to the frames I've extracted and the features I have picked and their sequence, this belongs to burglary, which then gives us that it would give us burglary as a predicted result, which is the 6th step. So maybe to conclude with this first architecture, it usually works by first understanding what appears in each frame using the CNN, and then it understands how what was appearing unfolds over time using the long short-term memory. So it firstly identifies the spatial features, and then it analyzes them over a temporal pattern. That is CNN plus LSTM. And then for our next architecture, we are going to go to the two-stream CNN. The two-stream CNN. Yes, right there. That is the two-stream CNN. And of course, just like the first architecture I chose, which was the CNN plus LSTM, it still begins in the same way with video input. Because now for the two-stream CNN, it's still a neural network. But unlike the standard CNNs that only analyze images, for this kind of CNN or model, it processes two different types of information from the video at the same time. And firstly, it is our step one. It begins with video input, just like the previous model. It first receives the clip from our data set, and each clip will contain footage labeled from our three classes. It will still do the same thing, which was our step two in the previous model, even here, which is frame extraction. And here it will extract frames or images from each of the videos, but it will still extract the same number of frames per video to ensure that the model will receive consistent input. So when it gets to the spatial stream, where it splits, after frame extraction, it splits into two streams. And for the spatial stream, it will process specifically the RGB frames. And the purpose of this is to identify objects and scene appearances. For example, let's say cars, people's doors, or buildings. On the other hand, for the temporal stream, it will process the optical flow, which usually represents motion between consecutive frames. On the other side, which was the RGB, it was processing objects and their scene and their appearances. On the other side, it is processing motion. It's analyzing motion for the temporal stream. So after each of these are extracted, still run them through the pre-trained CNN. It will still run them through the pre-trained CNN before. Yes, we'll still run them through a pre-trained CNN. Even for this one, we used a RESTnet 18. We used the RESTnet 18. And each of these streams will use that pre-trained CNN to extract important visual features according to its primary purpose. And then when it goes through this CNN, it will transform those raw images into future vectors that represent meaningful patterns. And then after all that has been done for both sides, it takes us to the next step, which is future fusion or concatenation. And the outputs from both streams, the spatial and temporal, are combined together. This allows the model to understand both what objects exist and how those objects move. And then it will go on to pass them through the fully connected classification layer, and the model will predict whether the video contains burglary, vandalism, or no for our case. So it will predict and give us an output. Which is the result. And then, yes, so we will go to evaluating both models to see how each performs. For my case, I used a confusion matrix which shows you both the false positives and false negatives. It shows you true negatives and true positives, false positives and false negatives. And it will help you compute metrics such as the accuracy, which is how many accuracies when it comes to model training is basically what proportion of the total predictions is right. That is all about accuracy. Precision, on the other hand, is what proportion of the would be true positives, what proportion of the actual positives has been predicted as true, has been predicted correctly. Recall, on the other hand, is what proportion of both the true positives and false negatives has been predicted as a true positive. So recall is basically of the many of the positives that exist. How many of those did it identify? And of course, the F1 score, which brings about a balance between precision and recall. And then I included the ROC curve. And the purpose of this is that it tells you how good the model predicts each class separately from other classes. And I think it gives us the most precise distinction for these two models, because you may not understand so much from the confusion matrix, but when you plot the ROC curve, from my screen, you will see that when it comes to burglary on the side of the CNN LSTM, it tells you it can predict burglary to 0.63. And the way this curve works is that it works on a scale of 0 to 1. So the best prediction must have a score of 1. The lower it is below 1, it means that the model may actually be guessing and not predicting. So if you see now, for example, on my CNN LSTM, the first architecture, it says it predicted burglary by 0.63. On the other side, it is 0.67. It means that the second model is predicting burglary better. It's separating burglary better from the other classes. When you see normal this side, it has a 0.59. When you go on the two-stream CNN, it has a 0.88. It means that still the two-stream CNN is predicting the normal class separately from other classes better than the first. And when you go to the last class, which is vandalism, it predicts it by 0.6. And on the other hand, of two stream, it predicts it by 0.79. So still, the two stream predicts the vandalism way better than that CNN plus LSTM. So in my conclusion, if I was to choose between the two, I think I'm going for that two stream CNN, because it can actually tell the classes apart better than the first model. Yes. Thank you so much.